So welcome everybody to our next talk, which is by Melissa Zhang. This is on Upsilon-like invariants from Khovanov homology. Thank you very much, Melissa.
Oh yeah, thank you. And thanks to all the organizers for inviting me to speak here. And also thanks to everyone for sticking around despite the vast variety of time zones. Okay, so I would like to give a survey on an algebraic construction on homological not invariants. I do come from low-dimensional topology, so half of my brain is saying like we should think about what these applications are. But really my personal motivation is that you see a lot of constructions done on knot-Floer homology or Heegaard-Floer homologies in general. And although the two theories, Khovanov homology and Heegaard-Floer homology, come from different foundations, algebraically, it seems like you can do a lot of the same tricks to both of them. And of course, there's triply graded homology, which relates the polynomials that you are actually categorifying here. So there's very good reason to be looking at this. This is based on joint work that I did with Lin Truong, and then also some separate ongoing work with Ross Akmachin. Okay, so just to warm up, I'm assuming that people in this session are somewhat familiar with Khovanov homology. And it's not so important to me that you know the actual definition of these things as much as you can catch on to the pattern that I'm going to be looking at today. So just to get us started somewhere, I want to frame the definition of Rasmussen's S invariant from Khovanov homology, actually Khovanov-Lie homology, of course, as coming from the data of a chain complex with a total differential and some filtration grading. So the pattern for today is that I have a chain complex, but it's going to be kind of special. It has a finite distinguished basis. And with respect to my filtration grading, these generators, the distinguished basis, are homogeneous. And then I have a differential consisting of multiple pieces. And perhaps it does something different with the grading, but it only goes in one direction. So it filters, the grading filters a total differential, which is why I'm putting this little subscript here. So if I wanted to form, or if I wanted to formulate Rasmussen's S invariant in this point of view, I could say that C is generated by the Kaufman states. And then I have the Khovanov differential, which preserves quantum grading and increasing homological grading. But then there's Lie's perturbation, which does not preserve quantum grading, but is filtered with respect to that. Okay, so this is my filtration grading. And then there's, of course, one last step. How do you actually get S? You have to say, I'm measuring some distinguished class, and that'll give me my number. So I'm thinking about getting numerical numbers, numerical invariants out. There are actually many different ways to think about this. So I'm just going to briefly describe these equivalent methods. I already said we can think about the filtration grading of a particular homology class. So that could be the thing that survives to Lie homology, which is just two-dimensional for a knot. Or you could say, let's say you have some amount of torsion and you're over PID or something. You could say that I want the maximal grading of a non-torsion element. So you could take a non-torsion tower is what I'm going to call it. Or you can say I have induced maps, and at each filtration level I have some induced map, and I just try to measure what is the most extreme or the best level where like you can still have a non-zero map. So just trying to find the boundary of a range. But for the purposes of this talk, I'm going to focus on this point of view just because it's easiest to talk to people about. Okay, so this brings us to what does it mean that an invariant is Upsilon-like? To me, that means that you're extending a numerical invariant, such as Rasmussen's S invariant, to a whole family of numerical invariants. And a typical way of doing this is just to take multiple independent filtration gradings and then mix them linearly. So you're taking linear combinations of various gradings. We'll see a lot of examples throughout this talk, and my goal is to make it so that everyone understands what kinds of tricks you can play to get an Upsilon-like invariant. Right now, all I need you to think about is that you need multiple independent filtration gratings. Okay, so then it becomes a search for which grading should you use. So let's first look at the inspiration for this, which is Oshvatz-Dipshit-Szabo's Upsilon. So knot-Fuller homology is, you could think of it as the associated graded object, or like a filtration on Heegard-Fuller homology, which was defined by the first and third authors here, Oshvatz and Szabo. Knot-Fuller homology was defined by Oshvatz and Szabo, as well as Rasmussen independently. Specifically, I'm going to look at a complex that is called the minus flavor of knot-Fuller homology. And I don't need you to know exactly what's going on, but you should keep these two bullet points in mind. So the data is, I have a symplectic manifold with two Lagrangians inside it. And then in order to record the embedding of my knot inside my ambient space, I'm going to put down what are typically thought of as two base points. But perhaps with this audience, we should just cut to the chase and say that these are actually just divisors. And then you want to say, well, if this is the data of a 3 manifold, and this is encoding the knot inside it, how do I come up with a complex? So remember that generators in Lagrangian-Floer homologies are going to be intersections between these two Lagrangians. So you have to make sure they're transverse to each other. And then the differentials are going to count pseudo-holomorphic curves. So specifically for knot-Floer homology, this is what we have. CFK minus is a module over this 2-variable polynomial ring, but there is a symmetry between U and V. C, which is the chains, underlying chains for the chain complex, is just freely generated over this ring by the intersection points between the two Lagrangians. The differential is going to count holomorphic disks between the generators. And the reason why we have these two variables is that we have these two base points or divisors. So whenever your disk passes over, let's say W, you put a U coefficient in front. And then if it passes over twice, you put a U squared, and so on. So you end up having this filtration of the differentials by how many times they go over the base points or intersect with the divisors. So in my mind, I would have a picture like this. And I know my graph is going to look kind of funny because we don't usually think about the axes looking like this, but here is my U power. And this is my V power. And then I can imagine a complex looking like this. Okay, and then maybe there's another generator at the same spot, but with no differentials coming out of it. I can slightly modify this, and for those of you who are familiar, knot-Fuller homology categorifies the Alexander polynomial. So the Alexander grading is like the analog to quantum grading in the knot-Fuller side. And the Alexander grading, I believe, is 1/2 of the U power minus the V power. So you can change the basis a little bit of this picture and get something that looks like, oops. It's still going to be symmetric between the two axes. You can do an Alexander grading here and then U power here. And it turns out you can still get this kind of nice looking complex. And the idea behind this upsilon in particular is that instead of just saying, I'm going to take my Alexander grading and take all of my filtration levels as, oops, that's probably backwards, as perhaps something like this, let's tilt the boundaries of these filtration levels and make the boundaries be diagonal at some slope. So I can,
Melissa, can I ask you a question? Sorry.
yes.
Sorry. So I'm not very familiar with this whole entire construction. So when you say intersection of Lagrangian, so I'm imagining like two Lagrangian knots. What is that? Is that correct? Right? What do you mean by intersection points? Sorry.
No, don't worry about it. I can, yes, I realize I'm not actually talking about Lagrangian like knots. It's very high dimensional.
Okay, so maybe what do you mean when you say Lagrangian? Because maybe I was interpreting this incorrectly.
Yeah, I can talk about that. So I'm going to use this space, if you don't mind.
Sorry to derail you. It's just like
no, it's fine. I always make my talks with enough time for people to ask questions, so they end up being short if people don't ask questions. Let's do a very, very simple version. So I think the trefoil or something is a knot where you can actually do it on the symplectic manifold that is this torus. In general, you would have like multiple tori multiplied together, so it's a higher dimensional thing. But when you're dimension 2, the area form is like your symplectic form. Okay, so this is my surface M. And then I'm probably going to draw this wrong, but here's one Lagrangian. So everything's Lagrangian when you're in dimension 2. And then you can do something like this. And I can add 2 base points, like one here, one here. I technically need a hole over here, but you can ignore that. Yeah, so now you exactly see the base points and you see the intersection points. So you can count the discs on this.
So intersection between the discs, you mean intersection like that red disc that you're drawing?
Intersection between Lagrangians are the generators. The discs are going to be the things that travel between intersections. So for instance, here is a disk. It kind of has sides on the Lagrangians. Yeah.
Cool, thank you.
No problem. Okay, any other questions? All right. That was a good time to stop me as well, because I was a little bit floundering with the description of my UV versus algebraic and Alexander. But the point is that there's this nice symmetry, and it basically comes from the fact that you're making a choice of like whether the knot, like how to parameterize the knot in here. Anyways, so GRT is going to mix your U power and V power filtrations, which gives you a range of slopes. And if your complex looks something like, let's say this is like the complex for the trefoil, you can then say, well, I can take my filtration levels, which have some slope, and try to measure some distinguished class. Now, in this picture, technically you have to multiply by, it like keeps going. I only drew one copy of the complex, right? It's actually over this polynomial ring. But let's say that I know that the total homology of this thing is one-dimensional. And I just kind of want to say like, okay, at what maximal GRT filtration level does the homology survive? Okay, so I'm not going to focus too hard on what the distinguished homology class you're measuring is, but the point is that you can draw these slopes and change your filtration by a single parameter to get a whole range of numerical values. Okay. So here's some notable properties of Upsilon, which is from Knopfler homology. First of all, it only changes at a couple of points. It's piecewise linear, and this is because your complex is pretty simple. I said it was finitely generated by just a couple of, intersection points, whatever you want in your theory. So when your distinguished homology class changes, like the cycle that represents it as you change your grading, then the slope might change, but it's generally a pretty simple function. So you could just write down the slopes and record where it starts And that's all the information that's in it. Also, it's a homomorphism, interestingly, from the smooth knot concordance group to R. And this is either interesting to you or not, and I don't have time to describe why it's interesting. But it's interesting maybe that in knot floor homology, connected sums of knots translates to in the categorified story, right? It's just a direct, just a tensor product. So you kind of have this, like if you have two knots and you connect some of them, then you just add their invariants, which is kind of useful because now you can do a lot of computations. As we'll see with a lot of these invariants that we're looking at today, such as Rasmussen's invariant, you also get a four-ball genus bound, which is of course related to this. And then this also gives you a non-orientable genus bound. So if you want to bound your knot in the four-ball with something non-orientable, you can also think about that genus. Okay. I should say here that the fact that this is a homomorphism was very much emphasized, and it's sort of like a very interesting thing because then you can study the structure of the knot concordance group. But this is of course not actually true in Khovanov homology. So what we want to do is the following. We want to think about what an Upsilon-like invariant from Khovanov homology would look like. Now, S is a homomorphism, but because Khovanov homology doesn't have this same Kunith formula, I actually don't expect this to be I don't expect an Upsilon-like invariant necessarily to be a homomorphism from the concordance group. What I do want is to play to the strengths of quantum invariants in general in order to find the gradings that I want to mix together. So as you've seen many times throughout this and last week, there are a lot of strengths of quantum invariants that we could look at. So first of all, we know that there are representation theoretic foundations. So we can think of everything in terms of that. In particular, we could think about, well, what if we use a different Lie group? So instead of SL2 homology, we can look at SLN homology. There's also a strong connection between quantum invariants and just braids. So we could then use it the other way and say, what does my Upsilon-like invariant tell me about braids? There's also the notion that Khovanov homology is kind of bigger than Floer theories. So for instance, there is a spectral sequence from Khovanov homology, reduced Khovanov homology to Heegard-Floer homology of the double-branched cover of a knot. Well, I guess on the left, it's technically the mirror of a knot, and here it's not. There's also spectral sequences like this. This is by Oshima-Sabo and this is by Dowlin. The point here is that all of the pages in between Khovanov theories and the Floer theories are invariants. So we can also use those spectral sequences as part of our grading information that we want to play with. Also, so why do we want one from Khovanov homology? Well, it's going to give you probably different information than Upsilon does because Upsilon is from not a quantum invariant, it's from a geometric invariant. Okay, so there's this idea that we want to use these things for the same reason, but they might have different information. Okay. So here is the first example in this survey. This is Levark and Lob's Gimel from SLN homology. This is not a lambda. This is the letter on the dreidel at Hanukkah that you really want to get because then you get more chocolate. And this is going to be associated to SLN homology, specifically with this polynomial as the potential. Okay, so let's leave that at that, and then I'll get back to why they have to use that potential. So the complex is just going to be the SLN complex. And then you want to take a mixture of gradings. So obviously the quantum grading is super useful because that's always there. But then there's this thing, the X power grading. Now, if you factor this, it's going to be X to the n minus 1 times x minus 1. So that means that it's kind of like this is the part where you're going to have an x power grading. And then there's this, what are you measuring? Well, there's this, roughly speaking, like a copy of SL1 homology in there, which you want to measure. So that gives you something concrete to actually measure the grading of when you look at the filtration. Okay, so one important thing about this invariant is that quasi-alternating knots are not that interesting from the point of view of Upsilon, but Gimmel is interesting for quasi-alternating knots, and they actually wrote a program to compute it and found an example where Gimmel detects, well, Gimmel is able to distinguish things. So this supports the idea that quantum invariants might give us different information when we come up with these numerical invariants. The next one that I want to talk about is related to the fact that there are a lot of spectral sequences from quantum invariants. So this is called Shachart-Seed-Szabo's generalized Rasmussen invariance. And to understand this, we first have to ignore this right-hand side because it's not as complicated as it looks. But just think about this again in the pattern that we've been thinking about today. You take the Khovanov chains just as usual, but you're going to make a total differential, which they call F-tot for filter total. That is a conglomeration of two existing things. So DSZ is actually Szabo's geometric spectral sequence, which is a combinatorial guess for the first spectral sequence that we knew about from Khovanov homology to Heegard-Floer homology. And this is basically this top section here. So what you're seeing is there are differentials for every homological degree based on, like, say I see a picture of this thing and I see a bunch of crossings between two circles. And if there are n of them, then I'm going to have a length n part of my differential. So this is why the homological grading is a filtration for Szabo's geometric spectral sequence. This part is called the Barnaton perturbation, but it's actually like a generalization of Barnaton's perturbation. I don't know if most of you think about Lie homology and Barnaton homology as being just over a different Frobenius algebra, but the first way that I was introduced to it is, well, you have Khovanov homology, and a merge map might look like this. So here's one x, y, x, y, and one in z. Let's do it this way. So you have two circles merging into one, and I would draw the picture like this. This is one tensor 1, x tensor 1, one tensor x, and x tensor x. And I can think about the differential for Khovanov homology as looking like this. If you perturb the Frobenius algebra so that the roots are actually different, you get to Lie homology, and the effect is like adding this extra arrow. Okay, and then for Barnaton homology, you actually add an arrow that looks like this. And that's effectively what this guy is. But there's also longer arrows in the homological direction. So you're going to see things like, okay, if you have two x's and they merge, it becomes just one x. And dually, you'll see a single one splitting into a bunch of ones tensored together. So this is effectively what their generalization is. Okay, so now that we know about the bidegree of these two pieces, we know that this thing also messes with the quantum degree. And we also know that this thing, they both have non-trivial bidegrees. So that means that both the homological and quantum gradings are actually filtration gradings. And so Shachart-Seed and Szabo were able to just mix those and come up with these invariants. So now let me talk about the annular refinements. And by annular, I just mean if you have a knot drawn somewhere, draw it on an annulus instead. So that just means there's something that you shouldn't cross, and then you draw your knot there. Obviously, one good example would be braid closures, and we're going to study them using these invariants. But let's just start with why we even think about annular refinements. Well, I should say that first of all, annular Khovanov homology, which is the basis of a lot of the stuff I'm talking about later, was defined by Asaida Shikora. They were studying mostly not just the annulus, but you could have a punctured sphere, which is any surface cross I. The relationship between annular Khovanov homology and Floer homologies was studied by Lawrence Roberts, and then Grigsby, Licata, and Verley were thinking about more like SL2C actions on annular Khovanov homology. So the benefit of the annular refinement for Khovanov homology is that you actually have a lot more structure, like immediate, obvious representation theoretic structure. Okay. But this is interesting to topologists for many reasons as well, and I'm going to try to draw a picture. You can think of a braid as the mapping class group on a disk with n marked points, right? You just kind of move the points around. Right, okay, so like swapping these two would be like sigma 2 or something. And this is actually super important to topology because then you can study these things called fibered knots in branch covers of other knots. You can also, there's just a lot of things to do just from the point of view that braid group is actually just an action on the surface. If you further take away, so you're taking braids and then you are closing them, you get the braid conjugacy classes, and then you mod out by annular isotopy, and that gives you an annular link. Transverse knots are going to be taking that, so braid conjugacy classes, and further modding out by the positive version of Markov 2. So, of course, this is of interest to contact topologists. Transverse knots are just finer than regular knots and interact somewhat with the geometry of the contact structure. And then we can also think about the knot concordance group again, which is that thing I mentioned about like your homomorphism coming from. And the general idea is that you can put a knot inside a solid donut. Maybe let's draw a less trivial knot. And then twist that donut into the neighborhood of a knot. And in that way, we can study the group. It's like an operation on the knot concordance group. So there's a lot of reasons to specifically think about annular knots. Okay, so if we can handle annular Khovanov homology so well, maybe we should be thinking about one of our gratings that we're mixing in with the quantum grating to be an annular grating. And Grigsby, Licata, Verley showed that the Khovanov-Lie complex actually admits an annular, sorry, they were the ones who showed this, but they wrote this out. The differential breaks down like this into 4 different pieces with different quantum and annular bigratings. So by mixing these, you'll get something like this. So you have some generator here, and let's see. If your axes are something like quantum minus 2 times annular and quantum, then you get this picture of differentials that look like this. So you can imagine this is just one, this is like somebody's differential. But if you put a bunch of these together, now you can do that same trick as before, which is let's take our differently sloped boundaries of filtration levels and try to measure the things that survive Lie's spectral sequence. So this is how you define these numerical invariants dt, one for each t. So the reason why I mentioned Shakard-Seed-Szabo's complex before is actually not just because of the Floer relationship as an example. It's because the work that I did with Lin was basically saying that you can do the same thing with their complex. So it turns out that the Shakard-Seed-Szabo complex also admits an annular filtration. So that means that you can get annular link invariants from their complex just by adding the same filtration grading that Grigsby-Licata-Verley imposed. And this just amounts to doing a lot of casework. You have to check like where in all of these configurations the center of your annulus is. And after checking this, you realize that you have a lot of differentials, but their bigradings are somewhat controlled. And if you mix the gradings properly, you can actually mix all three gradings now. So remember that Shakard-Seed-Szabo already were mixing the homological and quantum grading. So here we're mixing three different things, which leads us to a complex, or sorry, an invariant SRT from this square to R. The Grigsby-Licata-Verley and my invariant with Lin Truong have similar properties. You can use these to understand a lot of things that contact topologists care about because it's so good at handling grades. So I won't go through these, but they're just on the slide in case you're curious about why we wanted these invariants. In particular, I want to point out that Gage Martin was actually able to compute Rasmussen's S invariant for all three braid closures by using basically two big tools. There's Murasugi's classification of three braids, and then also the restrictions on the shape of this function dt. So you can imagine doing the same thing with this function. We haven't done it, but these are kinds of like interesting applications that came out of studying these. Okay, so here's a very new one that I am definitely not an expert on. But William Ballinger has what I believe is a very good like Upsilon from just SL2 homology candidate. So this is mixing homological and quantum grading, but the usual differential preserves quantum grading. So you want to think about what another differential would be. Well, first of all, you can have Lie homology, which doesn't preserve quantum grading. It's filtered. But if you want to add in the homological, you need to add a second differential that messes with that grading. It doesn't just increase it. So this is the D-1 differential from Rasmussen's E-1 spectral sequence. Roughly speaking, you should think of this as coming from Humphrey homology and going to SLN of your choice. So here, N is 2. Similar to Gimmel, there's no symmetry. But of course, Gimmel was a very useful invariant. So it could just be that this is telling you more information if it doesn't have symmetry. But I'm excited about this because there's analogs for both of these differentials in SLN homology. So perhaps one of you could study this and say, what kind of invariant do we get, like Upsilon from SL and homology? But not necessarily Gimmel, right? It's a different thing. Okay, and then finally, I have ongoing work with Ross Akhmechet about an alternative way of doing this. So coming from looking at not-Floer complexes, I'm actually pretty attached to this symmetry. And this is because the not-Floer complex, like the CFK with the symmetry, is actually used for a lot more purposes. There are different filtrations you can put on it. And for instance, you can compute the Heegaard-Floer homology of like large integer surgeries on a knot. I don't know what the analog is in Khovanov homology, but having this symmetry seems to be very important for some algebraic tricks. So our approach is that we're going to take another complex that is freely generated by the usual generators, over F adjoint UV. The differential is very simple. It's just very similar to the usual Khovanov differential. It's defined in a paper by Khovanov-Robert. Now, we also have these U power and V power gradings, not from some sort of like divisors, right, in the Heger-Fleur case, but rather just from the fact that we're assuming the roots of this polynomial live inside our ground ring. Okay, I should point out that Taketo Sano also studied this, and he has a Rasmussen-like invariant, not like an Upsilon-like invariant, but also using the U1 cross U1 equivariant Khovanov homology. So I want to point out here that our picture will look very similar. If you're familiar with, let's say, perhaps you're familiar with something like this, you would normally think, right, this is universal Khovanov homology. Instead of using H and T, we're splitting up H and T in terms of these existing roots. So if you would like, you could draw it like this. These red arrows come together as they add to H, and then the blue arrow is effectively T. And so our symmetry is actually just across this line. And then again, you can take your filtration levels, tilt them at whatever angle you want, and measure the thing that survives the homology. Okay. So there are a couple things I want to answer. Some of these I'm working on. Some of them I just want other people to look at as well. We, of course, are looking for a concrete example of what S alpha, this Upsilon-like invariant, will tell us. But we do have some idea of what the different slopes represent. This is kind of getting into the details of it, but basically, whenever you have an S invariant that isn't immediately determined by like Lee's canonical cycle, you know that you have some sort of homologous relationship between two different cycles in the special homology class. And if you're able to jump up from the cycle that you can, as a human, see, then you're going to get a non-trivial slope. So we know that non-trivial, it's like not everything is just flat. But the question is, can you have a picture that perhaps looks like a mountain peak, right? Can you have something that perhaps looks like this? That would be interesting. And so you might want to study these slopes. So it's capturing just a little bit more information from your complex than if you just looked at S, which is like this number. The other thing is that there are constructions that make use of the UV symmetry. So even though in Khovanov homology, we don't know what the analog should be because we don't have Khovanov homology for 3 manifolds, it could be interesting to see what those constructions actually spit out. Like, what are they the invariant of? Okay, and that's all I have to say. So thanks for listening.
Let's thank Melissa. Does anybody have any questions?
So I'm not sure if I might have missed when you said this, but which of these invariants were concordance invariants? Sorry, like there's
All
a
of them.
difference
Yeah.
between
Sorry.
being concordance invariants and being additive. So could you remind me, like, yeah.
Yes. Actually, a lot of them are homomorphisms. I'm pretty sure. Well, I talked about 2 annular ones. So there's, what did I talk about? Gimel is, phi is a homomorphism. Like DT and SRT are kind of annular, so we don't have a concordance group. What is SU? I want to say that that is not I think it's not a concordance homomorphism, just because you know how like for Rasmussen's S invariant, to show that it actually is additive, you kind of have this range that the resulting like connected sums S invariant can be in, but then you kind of use the fact that you know it has to be like an even integer to say that it's a homomorphism. So when you have these ranges, like these Upsilon-like things, without a Kunith formula, it's very hard to prove that it's a homomorphism. The fact that Bollinger's thing is a homomorphism is very interesting, and I don't personally understand how he has this Kunith formula, but it does come from that. So that's all I can say.
Cool, thanks.
Mhm.
Okay, so if there's no more questions, let's thank our speaker again for a beautiful talk. Thank you very much.
Thank you.